Now, let's talk about filtering. Let's go back. We were talking about the filtering operation on images, and I showed you some filters and these things. Now, let's talk about the filtering on turbulent field. The first question is that, okay, how do I mathematically obtain the filter? We already know the general concept of the filter, for example, median filter, box filter, or something. But what is the mathematical tool for this? Uh, for the filtering, I have to remind you the energy flow, this diagram that we had before. If you remember, uh, we had the geometric scale, we had uh, capital L. It was a geometric scale somewhere in here, a very big scale, okay? And then after the geometric scale, I had this integral length scale, L, a small l, and I had the turbulent production in, as you see, in the integral length scale somewhere in here, and it was sucking energy from uh, mean kinetic energy, and then it took this energy and feeds it into turbulent kinetic energy. Okay, this is the energy flow. These arrows are the flow of energy. And then we had the smallest scales, eta, Kolmogorov length scales. And we have somewhere in between the uh, inertial subrange that you see in here. This is the inertial subrange. So we call some length as LDI, and we call some length as LEI. And this we have the dissipation range as you see in here. This is the dissipation range, and on the other hand, we have the energy containing range. So this is the energy containing. So these three different colors are again showed in the energy density distribution in here. So you have the energy containing range in here, and then you have the inertial subrange, which kind of is linear, and you have also here it's the dissipation range. So this D in here is used for dissipation, and this E is for the energy contained. So the process is like this. You have the production and then dissipation at a very small scales. Now, when we are doing the filtering operation, the same way we select the filter size of the elec, we have to select the width of the filter, and we call it cutoff length scale. This is called delta, cutoff length scale. So the filter width, this delta or the cutoff length scale, is typically chosen somewhere within the inertial subrange. So you have to choose it inside the inertial subrange. I chose it, for example, in here. And corresponding to this, if I draw this is the energy spectrum, energy density versus wave numbers. You remember this. So we have this distribution, and I chose the cutoff length in here. So to the left of uh, this delta, I mean in this side, I have resolved all of the structures. So I wrote resolved to the left. So the grid whatever grid that I'm putting on my um, field, it has to be fine enough to resolve all of the wave numbers that are smaller than delta. To the right of delta, as you see, I wrote modeled. I have to use appropriate models to represent the physics that is occurring, and which is mainly the energy dissipation. Okay, mainly the energy dissipation. Some part of the inertial subrange is in here, but mainly I have the energy dissipation. So this is the cutoff length. This is the elect size that I'm choosing. It has to be in the inertial subrange. Do we have any questions so far? Did you understand what I'm doing?
Yes, I understand, but I want to ask a question.
Ask.
Uh, do we decide this cutoff length scale when we are doing this kind of calculation, this kind of
Yes.
simulation?
We decide on the size of the cutoff length scale.
Okay.
Yes, we will see it. Okay, so we started to talk about LES, and just to summarize, the equations are written in terms of filtered variables, filtered velocity and filtered pressure, because I have Navier-Stokes equations, and in Navier-Stokes I have velocity and pressure. So I have filtered velocity and filtered pressure. When you solve these equations, you will get the instantaneous filtered quantities. That's it. Now, I have to mention something about scale similarity. Again, you see these three pictures that you saw before. The colors are velocity magnitudes. And again, I told you it's one is a snapshot um, of a typical velocity field. So I said that the left one is a result of DNS data. The domain is a cube of size L, and it was exactly similar to what you get, for example, from PID measurements. The DNS means that it doesn't involve any modeling. The question is, okay, you have the left one, you have this data, DNS data. It is instantaneous velocity field, which is available to you. What it will look like if you filter this. We said that if you use a certain filter width, for example, delta is equal to L over 32, or if it is equal to L over 16, you will get two different filter fields. So, what do we mean by the filters? They are basically a cutoff length scale, we said. A cutoff length scale, we said that it is in here, so it is a kind of wave number that we choose. And then for wave numbers is smaller than the cutoff lengths, and which they correspond to larger eddies, you solve it, you resolve it. You have enough resolution in time and space to resolve them. For smaller ones, you just model them. So we know all of these things, and again, these are instantaneous fields. Okay, the original field and the filtered field, you see that they are different. We don't have any doubt on that. The question is this: when you are doing LES and solving filtered equations, the field you get is the filtered one. So you either get this field or this field doing LES. But in reality, in order to get the field the same as the original one, the same as this one, you need to somehow model the effects of all the details that are being lost. And we call them SGS model. So somehow you need to develop physics-based mathematical models to develop all these finer scale effects on the general filtered velocity field. And this is the whole idea behind the filtering. Some SGS models heavily rely on single filtered. Single filtered means just filter it once. This is single filtered. And some other heavily rely on doubly filtered velocity fields. Doubly filtered means you filter it twice. This is once, this is twice. Okay. In some of the approaches, they say since I have the difference between doubly filtered and single filtered fields, see when you have the difference between this one and this one, the difference of it is an image. Okay, they say okay, I have the difference between these two, so I can apply the same difference or the same model that is obtained from this difference to the original field and the single field. So it means between this and this. And actually, this is called the scale similarity. A scale similarity means that you assume you have the same dynamics between large scales and medium scales as uh, those that you have between medium and small scales. Did you get what I mean about the scale similarity? So the scales similarly change between uh, filtering operations. This is called the scale similarity. Understood?
Yes, I guess.
Okay. So we will continue about some of the mathematics of filtering operations. Okay, general filtering. This was, in fact, first introduced by Leonard back in 1974. And the idea is to obtain the filtered instantaneous velocity field. Have u tilde filtered instantaneous through the mathematical operation that I'm showing in here. This is the mathematical operation. What is this? Why on earth I need to understand the mathematics of this? Okay, it's just integration of g times u. What is g? I call g as a filter function. So um, you have to integrate or you have to do this integration over the entire domain that you have. And what we have is some normalization condition such that the integration of your filter function should be equal to 1. So if this happens, if you just take the integral of the filter function, uh, it shouldn't actually change your dimension or anything like that. This is why we call it a normalized function. So the simplest case is when we have homogeneous turbulence, like in DNS. The filter function for the homogeneous turbulence, as it is homogeneous, it won't be a function of a space anymore. So it is only a function of R. So what is R? Uh, you see the R is in here, so I will talk about this. So when the filter function is, I said it is independent of x, so I wrote g is a function of r. And during the development of this theory, there were lots of filter functions that were being used. Some of those are in here. For example, box filter or Gaussian filter and many other filter functions. But what does it really mean? You can roughly think about it like this. You have a solution grid. I'm talking about this grid. These points are your grid points. And at each grid point, you have velocity information. Each point. The question is, how you filter this velocity field. For example, consider the point, this point, as I write this point in here, consider this point in here, and consider that you want to use a box filter or moving average or blur filter, box blur, and you are using 3 by 3 or 9 points. So what you do exactly, it's you just sum them up, sum all of them, and divide by 9, right? To get the average of all those. And then you will replace the result on this point, on the original value of this point with the averaged value, let's say. So this practical thing that I showed actually corresponds to the multiplication of a certain filter function with the original velocity field. And this certain filter function, which we just used, is called a box filter, meaning that in order to obtain the filtered value for this point, you are using a box around it, this box with a certain width and height, and you use the values inside the box. That was a way to filter, but it's not the only option. For example, I can give some weight to the points, or I can use more points. Like instead of 3 by 3, I can use 5 by 5 or 7 by 7 box, and give more weights to the points that are closer to the original point, and give less weight to the points that are farther away from the central point. That is another type of filtering function, which is not a box filter anymore. Okay, box filter is a moving average filter. So if the weights are distributed according to Gaussian distribution, then I call it a Gaussian. And the width and also the height are basically your filter scales that you are trying to use. So you will probably have some. Uh, I could probably define a term project for you to apply some of these filters to original velocity, a typical velocity field, and um, let me think about it if I can prepare a term project out of this for you, and then you will have to deal with these kind of things. So applying a box filter, we just showed to you that it results in a blurry image, blurry velocity field. And after you apply this box filter, you keep losing the details because you are you average it out. So instead of 9 points, you see that you use a bigger filter, for example, a 5 by 5 or 7 by 7. I mean, 25 or 49 points, you will lose more information. And this is actually a rough understanding on how we apply filter function in large eddy simulation. So, for all the things that I have explained, how do we formulate in mathematical language is something like this. I don't know what are these here, so just don't forget them. Uh, Uh, I have a filter function g, and it could have a box shape, it could have a Gaussian shape or whatever. Then you apply it to your velocity field. This is your velocity field. And you have to note that in general, I said g is function of r and x both. And this means that you can use one filter function at one point and use another function at another point. And because it is a function of x, is a function of R, and I showed you what is R. R is this. So uh, it is the distance from the original point, the distance of another points from the center point, original point, and the filtering process is this filtering process is actually the essence of LES. So again, remember that I had my residual field equal to the difference between the instantaneous field and the filtered field, right? So my u prime is nothing but u minus u tilde. If you subtract the single filtered field from the original field, you would get a residual velocity field. And where we show uh, it as a prime by prime notation. And remember that in Reynolds averaging, uh, you had u prime, and this u prime was used for the fluctuations, right? And we said that there is a characteristic there that u prime bar for the rants is equal to 0. But in LES, u prime, as you see, it's used for the residual, but the average of the residuals of LES will not be 0. Keep in mind. So you cannot use this equality to 0 or this mathematical property in LES because you want to apply this, you want to apply such thing to your original momentum Navier-Stokes equations to obtain the governing equations, governing conservation equations for U tilde. When we are applying the filtering operation, we will see that such terms are there and they won't be equal to 0 anymore. Okay, let's continue. Okay, these are some properties of filtering operation. The first one, property. Uh, okay, it says that du dt tilde is equal to d dt of u tilde. What does it mean? It means differentiation commutes. In other words, if you take the time derivative of the instantaneous velocity and filter it, it is the same as getting the time derivative of the filtered velocity field. This one. The second one says that filtering and averaging they commute, meaning that the filter of the averaged is equal to the average of the filtered. And there is another property which is about the gradient, a special gradient. And you see that it says dui dxj filtered is not equal to ddxj of ui filtered. In other words, if you want to apply the filtering operation to the velocity gradient dui dxj, this will not be equal to the gradient of the filtered velocity field. Again, always remember the pictures that I have shown you. If you take the gradient of the data and then filter it, on the other hand, you have first filter and then take the gradient, you will see two different things. You will see two different results. So I think that for that term project, this could be another exercise to try this on some image and see if it gives the same thing or not. So we're going to use these properties in a while to obtain the filtered momentum equation. In order for you to visualize in your mind, now I will try to explain in a very, very simple way. For a very simple one-dimensional velocity field, meaning that you have only u of x, and x is from minus infinity to infinity, you will define one-dimensional box filter. And one-dimensional box filter, the definition is like this. So g of r is 1 over delta h of delta over 2 minus magnitude of r. So what is delta? Delta is the length scale, a certain length scale. It's not zero, and it's not zero within this delta, and everywhere, as you can see, it is zero on this here. And the h is Heaviside step function, unit step function. You remember what is this? So you get this filter and put it in the equation that we just showed before. This equation, you put the box filter in here, and you will find the filtered field. You will find this u tilde, and it will give you the spatial average in the interval of x minus delta over 2 and x plus delta over 2.